So, previous session, I guess the main message was that sometimes it's not obvious, like your intuition fails on trying to detect whether a particular language, a particular set of strings, is regular or non-regular. And so you need some more rigorous way to be sure whether a language is regular or not. And so you need some kind of mathematical proof that's more rigorous. And the theorem that's used is called the pumping lemma. And it's quite famous in theory of computation. So the idea is, if your language, and here's the central idea, okay, so concentrate. If your language is regular, then its strings can be pumped. Okay, you don't know what that means yet, but just remember this so far. So that implies that if you find strings in your language that cannot be pumped, then that language is not regular. I'm using here the mode of logic called modus tollens, which goes if A then B, but you're given also not B, well, you can then conclude not A. For example, if you live in Xiamen, that's the city in China that I live in, but if you live in Xiamen, therefore you live in China. But you don't live in China, therefore you don't live in Xiamen. Okay? So it's that kind of reasoning. So if your strings, so if your language is regular, its strings can be pumped. But let's say your strings cannot be pumped. Therefore, your language is not regular. In other words, it's a non-regular language. That's the essence. So what we need to do now is understand more about this concept of pumping. What's that about? And there'll be a theorem, pumping theorem, that is usually called the pumping lemma, because I guess it, when it was first discovered, it was part of a bigger proof, so hence got the label lemma. Right? So let's. So if you want to prove non-regularity, you can use the pumping lemma. So all regular languages, they have a special property related to pumping. Still being rather vague, but trying to give you the overall logic at the moment. Okay. So all regular languages, they have a special property. So if some language you're looking at does not have this special property, well then obviously it's not regular. Right? That's modus tollens, the reasoning I just gave you before. Okay? And what is this property? Well, it's that all the strings in the language can be pumped. So all the strings in your regular language can be pumped. You still don't know what that means yet, but we're getting onto it. Here's the theorem statement. Getting close. Okay. Okay. So what does it mean to be pumped? Well, here. Now, for them to be pumped, they have to have a certain minimum length. So if you're going to pump a string, it has to have a certain minimum length, and that length. You remember the length of a string? definition. It's the number of symbols in a string. The number of like if you just count the number of symbols in that string, and that's its length. Okay. So if your strings have a certain minimum length called the pumping length, then those strings can be pumped. And what does that mean? So, well, it means that you can take a section of, a substring, if you like, of that string, and you can then repeat it. So you concatenate, like here's your string, and let's say here's the substring. So you take that substring and then you make copies of it. So and insert it into the string. So you take your substring, make a copy of it. Let's say so now you have two copies. So you have one copy here, and then you'll insert it next to here. So you get a repeat. So now you have like two copies of that substring, and you can do that k times. Right? So you have 1, 2, 3, 4. And so, in effect, your string's now been pumped, in a sense, into three parts. So you can guess now where the word pumping comes from. You're just increasing the number of these substrings. You're pumping it up, so you're making it bigger, if you like. So you're increasing the length of your string. So your string now effectively be constituted of three parts. It'll be the part before the substring that got pumped, then the result of the pumping, the multiple copies of your substring, let's say k of them. So you'll be substring 1, the first copy, and the same substring again, second copy, and so on, k times. And then the third part will just be, what's left, effectively. Right? So the pre-pumping part, the pumping part, and the post-pumping part. Okay. So. So theorem 1.70, called the pumping lemma, was theorem lemma. Okay, so that's its traditional label, but Sipser puts it as a theorem. So 1.70. So now it's a bit detailed, with a lot of little details. So you need to pay attention. A little bit dry, but important. Okay, so you have a regular language called A. Right? So if A is a regular language, there's a number P, right? The so-called pumping length. Where if S is any string in that language, okay, that has length at least P, the so-called pumping length, right? Then, so we have a lot of ifs. Okay, there are two ifs here, like. If A is a regular language, there's a number P, the pumping length, where if, double if, right? It's not a trivial theorem statement at all. It's a lot of details. And it gets down to here. Yeah, so it's quite a long. I think this is our longest theorem statement so far. Okay, it gets a bit harder, right? So where if S is any string in A that has length at least P, at least the pumping length, right? Then that string you can divide it into three pieces. Here's your string S, and you divide it into